Hello guys, so for chapter 4, we're gonna take a look on building, drawing bending moment diagram and shear force diagram for frames. So in this chapter, we're gonna take a look on the internal loadings at a specified point, and then shear moment functions of that point, and then diagrams for that point, shear and moment diagrams for the beam, and then the frame. Then lastly, we'll take a look at the method of superposition. So internal loadings at a specified point. The internal loading at a specified point in the member can be determined by using method of sections. Almost similar to method of section in truss. And when you are sectioning the member, there will be normal forces, shear forces, and then a bending moment. So these three forces that you're going to find the value. It's a sign convention, although the choice is arbitrary, which is subjective to the one that doing the analysis. But the convention shown has been widely accepted in structural engineering. So mostly we accept this as a positive. If your shear is downward and then your normal is outward, and then your normal forces is perpendicular, going outside from the section, and then your moment is on um, counterclockwise, so it is considered positive. So as we discussed before in the trusses, or the forces acting when you're sectioning this, you should sectioning this member into two parts. So each force member will be counteract to each other. It will be the opposite of each other, as you can see here in moment, and then also on this normal forces, and then this shear force. So this is considered as positive. If you see, this is considered as positive. So if you are if you are sectioning here, and then your shear force is acting upward, so it's considered as positive. Same goes to normal. If it is in tension, or this one, it is actually member in tension. This one, when your normal force is acting upwards of the member, it is the uh, tension. So member in tension we consider as positive. And then moment, if it is some say concave, when your member becomes, you know, bandwidth concave like this, is considered as a positive, instead of you can have a member like this, which is due to moment of moment here is is producing a beam that is flexing flexing upwards, in opposite of concave. So this will be considered as negative. So sign convention is important because it affects your resulting moment, resulting forces. So we're going to take a look at the procedure for the analysis of internal loadings. Basically, when you are doing your analysis on internal loading, basically it's a step uh, in drawing your shear force or bending moment diagram. So this is like a small step in drawing the diagram. So the first thing is, number one is to determine the support reactions before the member is cut. So if it is a whole frame like this and being supported at these 2 points, right? So you need to find a reaction first. Then only you can cut the section. So first find the reactions. And then the second one, if the member is part of pin connected structure, the pin reactions can be determined using the method of section 2-5. You look into the textbook. So you can, if you have pin here, if it is a two-member frame, you can you can disassemble that member into two parts because you have a pin there, so you can determine the reaction. Keep all distributed loadings, couple moments, and forces acting on the member in their exact location. So when you are dismantling the member according to each member, so make sure that the forces is there based on the actual location, because it affects your reaction. Pass an imaginary section through the member perpendicular to axis. So you cut the section which is perpendicular to the axis of the member. At the point where internal loading is to determine. Let's say you want to find point here. So what you want to do, you want to find a point at C, for example. So you need to cut at C. You cut at C. And then draw a free body diagram of the segment. Let's say C here. Then you draw the free body diagram. Provided that you need to find the reaction first, then only you can determine the value at C, whatever the direction is. And then indicate the unknown result. So indicate here which one is N, V, M, and so on. You indicate acting in their positive directions. The first thing is when you want to assume, then you assume it is a positive. Then only if the answer is negative, then it shows that it is the other direction. And then moments should be summed at the section about axis that pass through the centroid of the member's cross-sectional area in order to eliminate normal forces and then shear forces, thereby solving M. So you take moment at the point, for example, point C. So take summation of moment at point C, get 0, so you can cross out the shear force and normal forces. So you can find M. So you can solve for M at point C, for example. So you take the moment here, so you can cancel out V and N. Cancel out. If the solution of equilibrium equation needs a quantity having a negative magnitude, as I said before, then the assumed directional sense of the quantity is opposite. So if you have negative answers, and then it is the direction is opposite. If you have negative moment, so it is in the opposite direction. So that's how you determine the internal loadings, internal moments. Yeah, so let's take a look at example number 4.1. You can find it in the textbook. So the building roof shown in photo has weight of 1.8 kilonewton per meter square and is supported by an 8 meter long simply supported beams that are spaced at 1 meter apart. So this is the 8 meter long simply supported beam. So each beam has shown transmits its loading to two girders, to these two girders. This is number one, and the end is number one, number two. Located at the front and the back of the building. So determine the internal shear. So V, you want to V, and then moment M in the front girder at point C. Point C here. So neglect the weight of the member. So the solution is first you determine whether it is a two-way or one-way slab. So the ratio give you this value, which is equal to 8. So your value is more than 2, so it is a one-way slab. L2 over L1. The tributary load on each interior beam, 1.8 kilonewton per meter squared times 1 meter, we get 1.8 kilonewton per meter. So this is your UDL, uniformly distributed loading. So as the spacing is 1 meter, and it is the roof weight is 1.8 kilonewton per meter square times 1 meter spacing. So you get 1.8 meter, and then reaction on girder. This is simple, 1.8, which is the UDL. then 8 meter is the length, and then divided by 2, then you get 7.2 kilonewton. And the 2H beam support 0.9 kilonewton per meter. So the 2H beam supported 0.9 kilonewton per meter. And then each column reaction is, you have 12, this is a length, 12 times 3.6 kilonewton, and then you have 11 times 7.2 kilonewton, then divided by 2, we get total is 43.2 kilonewton. The summation of Fy, you get 43.2 minus 3.6 minus 2 times 7.2 here, then minus the shear at C. So you can solve for C is 25.2 kilonewton. And with moment in anti-clockwise as positive, so summation of moment at C, take summation of moment at C, so you have 7.2 is 7.2 times 0.4 moment arm, and then 7.2 times 1.4 moment arms, and then 3.6 times 3.2.4 2.4 moment arm, and then lastly is the reaction here times 1.2 here. So you get your moment at C. So that's how you calculate your internal moments at a certain point, internal loadings at a certain point. So I think this question is quite straightforward. It's just tricky part would be to translate this 1.8 kilonewton per meter, supporting by 8 meter long supported beams. Translate this loading from the roof onto the this beam, these simply supported beams, and then from that simply supported beams you get this value. So this part is the tricky part, I would say, because you want to convert from that 1.8 roofing, the weight of the roof 1.8 kilonewton per meter square, then you times the 1 meter. 1 meter is the length between the support carried by the simply supported. I would say easier to distinguish between these two, the girder and the beam. So this one is girder, so it's beam. So supported by the beam is 1 meter length and then 8 meter long. It's shown here. So 1.8 times 1 meter, so it will be 1.8 kilonewton per meter. If you draw the free body diagram for this beam, will be like 8 meter, and then this uniformly is 1.8 kilonewton per meter. So you get your reaction here. That would be the loading on top of this beam. So that's why you times that UDL 1.8 kilonewton per meter from the roof times with the length of the long simply supported beam 8 meter. Then you divide it by 2 because it is supported on both ends. So you get your um, point load on the beam, like this one, like as shown here. So basically 7.2 here, reaction calculated here is actually applied on top of the beam. So that's how you'll get this value. So that's how. But the one that is difference is this one 3.6 because it is at the most the leftmost or the end beam. So the beam here would carry shorter, like half of the roof, half of the roof here. So this here will be 1.8 times 0.5, because the length here is 0.5. I think that is the most tricky part. And then that will be straightforward. Just remember that your assumption, shear, assume your shear down, and then your if moment, you assume it's counterclockwise, and then if it is normal forces, you should assume on a perpendicular, again going outside, or tension. But I think in drawing bending moment diagram, bending moment diagram and shear force diagram, SFD, we are only concerned only on these two elements, the shear force and then the bending moment. So always remember that you assume downward, so that uh, it is positive, as shown in the previous slide. This one, with downward negative positive, counterclockwise positive, tension positive. Next is shear and moment function. So design of beam requires detailed knowledge of variations of shear and moment in designing of beam, because failure will occur due to moment, which is bending failure, or shear, which cause deformation of beam lah. So usually we counter this with more stirrups, or bigger size beam, or larger diameter of steel reinforcement. So internal normal is generally not considered, as the loads applied at the beam act perpendicular to the beam axis, because the load is perpendicular, as shown, perpendicular 90 degrees. So for design purposes, a beam's resistance to shear and bending is more important than its ability to resist normal force. An exception is when it is subject to compressive axial force, where buckling may occur. So in the case of beam column situation, beam, beam column situation, where you have your beam, uh, where your beam might experience buckling, maybe due to slenderness, or due to very long span. So it may experience compressive axial force. So in that case, you need to identify the normal force. But most of the time, the design of beam is only on beam, not column beam. Shear and moment functions. In general, the internal shear and moment function will be discontinuous, or their slope will be discontinuous at points where the type of magnitude or distributed load changes. So this is an important, a principle. So internal shear and moment will be discontinuous at points where the magnitude changes. So example here, you have a distributed load here, and then it changes into point load. So this point, at point C, the functions will be discontinuous. So the slope, when you draw the diagram, there will be a discontinuity at that point. So let's take a look at the shear and moment functions. So procedure for analysis. First, you need to determine the support reactions on the beam, and then resolve all the external forces into components acting perpendicular and parallel to beam's axis, and then specify separate coordinates x and associated origins extending in two regions of the beam between concentrated force, or couple moments, or discontinuity of distributed loading. So you need to specify the point where there is a discontinuity because changes in distributed loading, and then regions of beam between concentrated force or couple moments. So the area where there is a concentrated force, there is a couple moments, so you need to determine the point. For example, here will be at point B, point C, and then lastly at the end point. And then section the beam perpendicular to its axis at its distances x. So you cut at that point of reference. We need to determine the point because there is a discontinuity. So from the free body diagram of one of the segments, determine the unknowns shear and moment. On the free body diagram, shear and moment should be shown acting to their positive directions, which is downward and then counterclockwise. V is obtained using Y equilibrium, and then M is obtained at the interested point. I mean, at the point of interest. And the results can be checked by noting that uh, the when you differentiate the moment function, you get shear, and then when you differentiate the shear function, you will get a force load, the distributed load. So let's take a look at example 4.4. Determine the shear and moment in the beam shown as function of x. So this function of x, this is the function that we want to talk about. When you put x value here, from 0 to 9, as shown here, 9 and maximum 9. So you get the function of the function of the moment and the uh, function of the shear here. So that is a function which is graph lah, which is a function of graph. So the solution, for the purpose of computing the support reactions, the distributed load is replaced by its resultant force of 135 kN. However, this resultant is not the actual load on the beam. So the resultant, this is the law for triangle distributing load. So basically, the triangle distributing load is it's like calculating the triangle 1 over 2 times 30 times 9. So that is the value of the load, and then the location will be two-third from the low, or it is located from the 1/3 from the maximum point. So that is law for triangular distributed load. And shear and moment functions. So a free body diagram of the beam segment of length x is shown. Note that the intensity of the triangular load at the section is found by proportion. So when you want to find out the intensity of the triangular load, it is a proportion. Let's say maximum here is 30, so it's 30 proportion to 9 meter. So if you want to know what is the value here, for example, so that value will be proportional to its distance here, x. So it will be a proportion. There will be a proportion here. So this is the proportion. So this is the result of the proportion. It will be 30 30 30 over 9 times x. So you get your 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 load here for look at x. If you put x with a 3 value of 3, or example you want to know at 3, so your value of distributed load, the maximum will be 10 kilonewton. So example here, you have 30 kilonewton here, but at 3 meter. Let's say this is a 3 meter. So your triangle here would be 10 kilo Newton per meter. So that's how the solution here come up with the value of 10x. This is a function, the function of triangular. So you can put anything here. 0 to 9, you can put 1, 2, 3, 5, 6. So it gives you the value of the triangular distributed load. So you put into your triangle resultant load, you should calculate like you calculate the area of triangle 1 over 2 times distance and then your height or your load at that point. So with the load intensity known, the resultant of the distributed load is found in the usual manner, summation of y, summation of x. So you can find your uh, resultant distributed load. Resultant distributed load is but the reaction, we need to find the reaction. So the reaction has been calculated. So this is your reaction. This is your moment because it is a fixed end, a cantilever beam. So you have shear here, and then you have moment here. So you cut at point. So the point that you're interested, the whole point, because it is a single type of load. So this is your shear moment function. This is your shear function, summation of y equal to 0. So this is your reaction. This is your reaction. Reaction at A. This is AY. This is AY. This is your AY. And this is your triangular distributed load, denoted as triangle. So this is your triangle distributed load. And this is your shear function. Shear at any section you cut. This one, shear V. So this is your shear function. You can get your shear value at any point from 0 to 9. That's the length of the beam. Then you put inside the value, you get your value of shear. So you cut here, and then you put that. Let's say this is 0 to 9, right? So you cut here, let's say this 1 meter, so you put 1 meter, 1x, 1 meter into here, so you get your value of shear. So this is basically a formula for your for that uh, set of loading. So what I want to highlight here is that the equation is uh, the equation is quadratic because it has a power of 2. So if it is a quadratic, so you expect a curve diagram like that, curve diagram. If it is there's no x here, if it is only one x, x to the power of 1, so it will be a linear graph. So if it is a power of 3, so it is a power graph. So for moment, summation moment at s any point. So this is your moment, the moment that you calculated, the moment reaction at A. Moment reaction at A. This is a moment at A. And then this is your shear, your reaction at A, AY. And X is the moment arm. And then this is your triangle load divided by times by the moment arm, which is 1 over 3 to them, because your beam here, and it is triangle, and you have a triangle here. So your V, your resultant, the resultant moment will be calculated. The moment arm will be here, which is x over 3. So let's say if your Triangle is the other way around. So the support is here, and support here. So your moment arm will be 2x, 2x over 3. So it depends on the orientation of your triangle. And then there's a moment arm, there is an arm, a moment at the point of that we cut. So you get, this is your equation for moment, which is to the power of 3. Uh, and do note that the different, when you differentiate the moment, will be equal to v. So you differentiate here. So 3 times 0.556 minus 1. So this will be cancelled out. This x will be cancelled out. So you get 135 minus 1.667 power of x power of 2. So which is similar. So when you should differentiate the graph of any moment, you get v. When you should differentiate v, you get your shear. You get the value of shear. You will get the value of distributed load here. Negative 10x to the power of 3 when you differentiate this equation. It is important. This is I mean when you master this shear, how to develop shear moment function, so you can basically draw any free body, any bending moment diagram or shear force diagram for any beams or frame. You can also solve it at the point of interest by not doing these functions, but by analyzing at certain point. So next, next we're going to take a look at the situation if the variations of VMN are plotted, VNM are plotted, the graphs are termed the shear diagram and moment diagram. So when you plot that functions, it becomes a shear and moment diagram, shear force and moment any moment diagram. So this will continue in the next video.